This is Brent with Lykins Motorsports, and this week's video is going to be about a few things. We're going to just talk for a few seconds about these cylinder heads. This is another 428 engine build that I'm starting for a customer in the Czech Republic. It's meant to go in another Shelby Cobra replica. So we're doing another one of those builds where the engine looks stock appearing on the outside, but has some really nice parts on the inside. Just like last week, we have another set of C6 AER heads, and I won't bore you with a lot of redundant details, but these have, again, the same treatment: the bronze valve guides, the SI stainless intake and exhaust valves, 11/32 stem, and we were able to use the same valve spring package, retainers and locks and locators as the other set of C6 heads. And the camshaft is pretty much exactly the same. So we were able to just basically duplicate the other set of heads that we were working on last week. So the CCs came in just a little bit different, like 2 CCs different. That'll be enough that I will have to compensate with the piston, because I'm basically trying to build both of these engines exactly the same with maybe 1 or 2 changes so that we can get a good A/B test. It doesn't happen very often where we have two exact same engines. So this is an opportunity to learn a little bit. So I'm going to take advantage of that opportunity. So while I was setting these heads up for the cam, I was looking at the cam card and thought that this would be a good opportunity to go over how to read a cam card. And a lot of you have been asking cam questions, and I get a lot of the same questions on the forums. So I think I'm going to put my camera in my tripod where I don't have to hold it for a few minutes, and we're going to go over the various aspects of this cam card. All right, I got my camera set up, and before I begin, I just want to thank everybody. I have surpassed 1,000 subscriptions and way over 5,000 hours of viewing time. And I know in comparison to a lot of the YouTubers out there, it's a drop in the bucket, but it's a lot for me, and I appreciate everyone watching and listening and hitting that subscribe button and those likes. So this is just an example of a Comp Cam's cam card. This is the cam for Jindrik, who is in the Czech Republic, and this is a billet core hydraulic roller camshaft for a Ford FE. And you can tell by this groove here on the number 2 journal, and there's also a groove on the number 4 journal. That's for if you stick this cam in a side oiler block so that you can oil the rockers. The oil uses this annular groove, and that's how it gets up to the cylinder heads if you choose to oil that way. So I'm just going to roll through each line on this cam card, and I know I won't be able to explain every little thing, but this is just going to be a basics, some camshaft talk and some cam card talk. And the first thing that I come to is this part number 33-000-11. The 33 is the engine type with comp cams. So 33 correlates to a Ford FE. I think a number 35 is a Windsor, and there are some others that I do a lot of FE, so I'm used to seeing that 33. But the -000 means it's a custom, and I pretty much use, well, I don't know the last time that I used a shelf cam. The custom cams are just, that much more superior. The -11 means that's the core number. This is a steel, a billet core. You'll see some -9s and some -11s for the billets. and they correspond to the grade of steel. I think these are 8620s. I could be mistaken. But, you know, why do we use different cam cores, or why do we use different materials? And, you know, you can basically narrow it down to the strength of the cam. A cast cam, like you would see in a flat tappet, or in some of your, you know, austempered iron hydraulic cams and such, you know, those have, you know, a functional limit on what they will withstand as far as valve spring pressures and that sort of thing. So when you really start getting into, you know, the higher performance applications, all of your camshafts will usually be a billet core material, a billet steel. Your flat tappets will usually be, you know, a cast iron, a cast core. There's some, I guess, exceptions to that rule. A lot of your, well, NASCAR doesn't run flat tappet anymore. They run solid rollers. But it used to be that their solid flat tappet camshafts were steel cores, and they would run ceramic lifters. That's kind of a, you know, an outlier. But so this is a billet steel core. It's got the serial number, so if you ever need to, you know, look up, call your comp cams rep and pull up a serial number, they can see exactly what's done to it. The engine is the next line. It says it's for a Ford FE 352 to 428. That's a general description. Obviously, there were engines in the FE class that were smaller than 352, and we're all the way up to, you know, some really big 530, 540 cubic inch FEs now. The grind number, these are the lobe numbers. You got to have a custom a lobe catalog to see those. But, you know, that's how I usually go through. I will go through Comp Cam's lobe catalog and pick out the intake lobe and the exhaust lobe to fit the application that I'm working with. The HR signifies it's a hydraulic roller. The 113 is the lobe separation angle for this cam, and it's ground with 5 degrees of advance. Before we get into any further, some more differences between flat tappet and roller. You know, the flat tappet stuff is cheaper. I sell custom flat tappets for $225. The lifters usually run anywhere from, you know, around $90 for your typical, what you would consider, you know, a regular hydraulic flat tappet or a solid flat tappet lifter. The higher end lifters from Crower and Howard's, you know, that have the EDM hole or the flat spot for hydraulics, usually run anywhere from $125 to $140. When you get into your really high-end flat tappet lifters, solid flat tappet lifters, you'll pay, you know, $350 all the way up to, you know, over $1,000 for a set of tool steel solid flat tappet lifters from suppliers like Trend. So, you know, it gets pretty expensive if you want to roll that way. Roller cams, custom roller cams start at $450, and then you pay $450 for hydraulic lifters, roller lifters. You can find some non-pressure fed solid roller lifters for, you know, around $400, $450. But your good solid roller lifters that have pressure fed oiling to the needle bearings, they usually start at $750 and can go on up from there. The pressure fed solid roller lifters are excellent for street driving because, you know, if it didn't have the oil pressure feed to the needle bearings, then you're relying on oil splash to keep those needle bearings from failing. And typically, if you don't have the pressure fed oiling, you can expect those lifters to last about 3,500 miles. The pressure fed oiling adds a tremendous amount of life to the lifter, and companies like Isky and some of the others advertise 30,000 mile intervals on their solid roller lifters. Another thing, the flat tappet cams involve a break-in period. And, you know, when we do that sort of thing, you kind of have to be on your toes when you first fire the engine up. The timing has to be perfect. The carburetor has to be perfect. You can't have too much valve spring pressure. You got to have a special break-in oil. You know, roller cam, you can pretty much just throw it in there and turn the key and roll on with it. So we're at the special instructions mark. When I have my custom cams ground, they always stick my name on there, and you'll see that on a lot of the cam cards. On some flat tappet stuff, you will see on my cams, you will see a line that will say max lobe taper. And I have that done as a default on my flat tappet cams. And max lobe taper means the angle across the lobe is going to be steeper than normal. A flat tappet cam has an angle across the lobe so that it will spin the lifter. The faster that you spin that lifter, the quicker that it will burnish the lobe and the bottom and face of the lifter, and the less likely that you will have problems with the cam break-in. So I do that as a default to all my flat tappet cams. You'll also see sometimes nitrided on the special instructions. Some will say, you know, on the small block Ford stuff that I do, it'll say the same journal from 1 to 5 because I use different bearings. Could be a 50 millimeter cam core, could be a 60 millimeter cam core. That will all be in that special instruction line. The next line is valve adjustment. This one says hydraulic. So obviously you don't have lash. If this was a solid cam, it would say, you know, 0.018 or 0.020. That would be your lash spec for that camshaft. Gross valve lift. This is how far the valve should open if you're in a perfect environment with no, you know, parasitic loss due to pushrod deflection, valve train deflection, poor valve train geometry, etc. So if you look down below here, I hope you can see this on camera. This 353, 358, that is the lobe lift. So you take that number and you multiply it by the rocker ratio that you're working with. Comp cams defaults their FE gross valve lift to a 173 rocker ratio. So if you're using a 176 or something like a T&D rocker with 1.8 or 2-to-1 rocker arm ratio, then you need to multiply this lobe lift by the rocker ratio that you're using. Then when you get that gross number, then you spend time as an engine builder to try to make sure that you get to, you know, as close as you can to that gross number. In my other videos, you see me trying to do different things, raising the stands up, lowering the stands, doing this, doing that, to try to get that minimum amount of sweep and get that geometry perfect. The reason I do that is because I don't want to lose gross valve lift to something, you know, that could have otherwise been corrected at build time. So you need to aim for that gross valve lift number. Let's see. The next thing we see is duration at 6 thousandths tappet lift. You will see that for a hydraulic cam. If it's a solid cam, you'll see duration at somewhere like 20 thousandths tappet lift. And this is called your advertised duration. And this is basically what we use for different calculations, such as dynamic compression ratio calculations, overlap calculations. In comparison to your 50 thousandths duration, this will also tell you how aggressive this lobe is. And I guess a technical definition of advertised duration, basically on this cam card at duration at 6 thousandths lift, this is how many degrees it takes to go from 6 thousandths tappet lift all the way until your valve opens and then starts to close and comes back down to 6 thousandths tappet lift. So we're at 280 degrees on the intake side, 290 on the exhaust side for advertised duration. These valve timing events, this is what we use to degree the camshaft. This would be used for your valve event method. The intake center line would be for your intake center line method. So I can do the valve event method, and I can compare when my intake valve opens at 50 thousandths lift, and I can adjust it one way or the other based on what the cam card says. So this one, intake valve opens 5 degrees before top dead center, closes 41 degrees after bottom dead center. The exhaust valve opens 56 degrees before bottom dead center and closes 1 degree after top dead center. So degreeing the cam, changing the cam timing, moves these numbers around. But this is where I had this cam ground, and that's where I'm going to aim for when I go to degree this cam later when it's in the block. Same thing with the intake center line. When I sent the specs in to have this cam ground, I told them that I want it on a 108 intake center line, so that's why this 113 plus 5 degrees advance is there. These specs are for cam installed at 108 intake center line. So if I use the intake center line method when I degree, then that intake center line should be at 108. So just a little quick math. Your lobe separation, your intake center line, and your exhaust center line are all mathematically linked. If I take my intake center line and my exhaust center line, add those together, divide those by 2, it should spit out your lobe separation. So you can use that when you're degreeing the cam. Okay, so we're going back. We see this one's 5 degrees advanced. Camshafts can be advanced or retarded or straight up. And advanced means your intake center line is smaller than your lobe separation. Retarded is when your intake center line is greater than your lobe separation. Straight up means your intake center line is going to be equal to your lobe separation angle. You will see this all over the internet, and it is one of my pet peeves. Somebody will say, I put this cam in straight up. What they are probably meaning is that they line the dots up on the timing gears. That really has no bearing on whether a cam is straight up or not, because you don't know if your cam is ground with advance, retard, or what. And technically speaking, if a camshaft is installed straight up, intake center line equals your lobe separation angle. So a lot of guys don't know that. Even some engine builders don't know that. Duration at 50 thousandths. This is what most people think of when they see cam duration. This is duration at 50 thousandths lift. So, you know, just as I explained the advertised duration up here at 6 thousandths lift, this is going to be your duration at 50 thousandths lift. So we start measuring this when the valve opens, or I'm sorry, the lifter basically rises 50 thousandths. And then it goes all the way up and all the way back down and stops when you're 50 thousandths from the heel of the cam lobe. So that would be your 50 thousandths duration. 225 degrees intake, 235 degrees exhaust. I look at the 50 thousandths duration as a number where the engine is going to peak the horsepower. So I can move this up and down depending on where I want the engine to peak. So for a horsepower peak of 5,000, somewhere around 5,000 RPM, 5,200 RPM, based on the size of the engine, based on the cylinder heads that I'm using, this is about what I'm going to need to get to that peak. So, you know, we're looking at what size cam is necessary for an engine. The displacement makes a whole lot of difference on what size the cam. Your goal with the camshaft is to fill the cylinder. if you have, for instance, the numbers up here, 352 to 428, that is a large displacement difference. This camshaft in a 352 is going to peak a lot higher than this camshaft in a 428 because this cam's function is to fill the cylinders. When the cylinders are smaller, then it doesn't have to work as hard. The peak horsepower RPM is going to go up on a smaller engine. The same with a cylinder head. A better flowing cylinder head, a better performing cylinder head is going to peak higher than a low performing cylinder head. Because if you think of it, the cam's job is to open the valve. The head's job is to pack everything into that cylinder, okay? So when you hold the door open, a poor cylinder head's not going to be able to feed the stuff in. When you hold the door open on a high-flowing cylinder head, you're gonna have lots of opportunity for stuff to flow in there. So I'll give you a real-world example. On my 352, I had the heads ported. The difference was about 44 CFM. With the same camshaft, the peak horsepower RPM went up 400 RPM when I ported the heads. That's because the cylinder heads were flowing better the second time, and it made it a lot easier for the cam to do its job. So, 50 thousandths duration is based on, 1, the displacement of the cylinder head, 2, the performance of the displacement of the engine, and 2, the performance of the cylinder head. And there are other variables involved in that, but those are the 2 biggest ones. Load lift, we've already hit on that. That's how much lift that each cam lobe has ground into it. You multiply that by your rocker arm ratio. Lobe separation angle. This is a pretty big component of how much overlap you have. Overlap is necessary for every application, and there's a target amount of overlap for every application. Guys like overlap because it gives you that sound. When the valves are open at the same time and the engine isn't efficient, it gives you that really radical sound that everybody likes. Unfortunately, if you get to a point where you have too much overlap, then you are pulling the intake charge in and you're pushing it right out the exhaust without converting it into mechanical energy. So changing the amount of lobe separation as well as the advertised duration changes the amount of overlap. You will see a lot of, this is another pet peeve of mine, you'll see things on the internet saying, oh, you need a 108 lobe separation for a drag race motor. If it's EFI, you need 112. If you have Weber's, it needs to be 114 and 115. That cannot be further from the truth. The lobe separation angle is a culmination of all the valve events. And it all depends on which lobe you're using and just a myriad of other variables. But do not look at the lobe separation angle with a general blanket statement like that, because it certainly doesn't work that way. On my FE cams, you'll see me use everything from a 106 all the way up to a 116. On some of my pull and charge engines, I'll run a 119 or 120. So the lobe separation angle is a result of all the valve events and you putting the valve events where you think it needs to be for the engine that you're working on. So, let's see, I've got a list that I'm going through here that I'm looking off of. The lobe separation angle combined with your advertised duration also affects the amount of engine vacuum that you have. And, you will see me jiggle the lobe separation angle around as well as the advertised durations if I need more vacuum for an engine or less vacuum, or if somebody doesn't even care. There are certain racing classes that have lift rules, and you have to watch how much valve lift you have. There are also certain classes that have vacuum rules that the engine has to produce, 22 inches of vacuum or 18 inches of vacuum. So all of that has to be designed into the camshaft. All right, that was a mouthful. That's a pretty good place to start. That's an overall view of camshaft design and how to read a cam card. And for Jendrik here, I have thoroughly went over his cam card so he can see what's going in his engine. And like the other builds, I will be focusing on a few videos down the road of assembling his engine. Just plan on doing a lot of cool things down the road. So if you have anything else that you would like to hear me talk about, I'm not saying that I'm the authority in any of this stuff, but if you have a specific subject that you would like to hear me speak on, you know, I will try to do my best to answer your questions or to do a video on that subject. So, again, this is Brent, Lykins Motorsports, and doing a whole lot of FE builds and got a whole lot of cool videos coming down the road. So hit that subscribe button, hit that like button, and thanks for viewing, and have a good weekend.